Hello everyone. In the previous lecture, we have introduced the one-dimensional consolidation test and the interpretation. So, how to calculate the ground settlement using the results of a one-dimensional consolidation test. This section, we will talk about calculation of settlement. Settlement of a structural foundation is caused by the ground soil deformation. Usually, the total settlement of foundation can be divided into three components: initial immediate settlement, primary consolidation settlement, secondary consolidation settlement. The elastic or immediate settlement is caused mostly by lateral displacement of ground under external load. It's assumed that no volume change because time is too short to drain away pore water. The primary consolidation settlement is caused by the expulsion of the pore water for the saturated soil, during which pore water pressure gradually is transferred into effective stress. At the end of primary consolidation, that is, after complete dissipation of pore water pressure, some settlement is observed because of the plastic adjustment of soil fabric, which is called secondary consolidation settlement. For ordinary clay soil, the primary consolidation settlement is the major part of the foundation settlement. The elastic settlement can be estimated using the result from elastic theory. Its magnitude depends on the flexibility of the foundation and the type of material on which it's resting. In engineering practice, the primary consolidation settlement is calculated based on soil compression under zero lateral strain condition. The one-dimensional method is divided into two types in terms of the coordinate scales picked for the plots of compression curve. One is the EP curve method. The other is the E-log P curve method. About the calculation of primary consolidation settlement, this section is very important in soil mechanics. Firstly, let's talk about the calculation of primary consolidation settlement based on EP curve. A thin homogeneous saturated soil layer of thickness h is considered under constrained condition. The existing average effective overburden pressure is sigma Sg, and the water ratio of saturated soil layer is E1, corresponding to sigma Sg. Then a uniform load P is applied on the soil layer, which results an increase of effective pressure sigma Z in the ground soil. The water ratio changes into E2 after application of external load. The stress increase let the primary consolidation settlement be S, so the change in the volume of soil is equal to the change in water ratio, which can be given by delta E. We can calculate the volumetric strain Uv from the change in water ratio. For one-dimensional consolidation, the vertical strain Uv is equal to volumetric strain Uv. We can write a relationship between settlement S and the change in water ratio delta E. Then, we can calculate the primary consolidation settlement using EP curve from the compression curve, read off the initial water ratio E1 and water ratio E2 after compression, corresponding to the initial stress P1 and the summation P2 of initial stress and the stress increase P. The settlement S can be obtained. According to the definition of a coefficient of compression, we can rewrite the settlement equation using alpha. Similarly, the settlement can be expressed in coefficient of volume compressibility MV or constrained compression modulus ES. The settlement of a thin homogeneous soil layer can be calculated using EP curve directly. Now, let's consider how about a thick heterogeneous soil layer. Layer-wise summation method is applied widely to calculate the primary consolidation settlement in China. There are several basic assumptions for this method. Contact pressure at the base of the foundation is disturbed linearly. Stress increase is calculated based on elastic theory. Deformation is only in the vertical direction without lateral strain. only primary consolidation sediment is considered. The ground soil is divided into several sublayers. The foundation sediment is the summation of the soil composition of all sublayers. The computational procedure for the layer-wise summation method is as follows. Step 1. Divide the ground soil several suitable number of sublayers. The interface among the different soil types and the water table should be the surface among sublayers. Each sublayer within a same soil layer should not be overly thick. The thickness of each sublayer, HA, should be controlled within 2 meter to 4 meter, or HA less than or equal to 0.4 times B, where B is the width of the foundation. Step 2. Determine the vertical effective overburden pressure, sigma V, on each interface of sublayers, and plot its distribution curve. The effective overburden pressure should be calculated from the ground surface. Step 3. Calculate the stress at the base of the foundation, P0, namely the net contact pressure. It should be noted, when the foundation has an embedment depth of D, the net contact pressure should be used to calculate the stress increase induced in the ground. The net contact pressure, P0, equal to contact pressure P minus gamma D. Step 4. Determine the stress increase, delta sigma Z, on each interface of sublayers, and plot its distribution curve. The stress increase should be calculated from the base of the foundation. Step 5. Take the average values of the effective overburden pressure and the stress increase for each sublayers. In this equation, sigma VIU and sigma VIL are the effective overburden pressure on the upper and the lower surface of S sublayer respectively. Delta sigma ZIU and delta sigma ZIL are the stress increase on the upper and the lower surface of S sublayers respectively. Step 6. Determine the calculation depth. Theoretically, the stress increase transmits to an infinite depth of the ground. However, in reality, when the soil composition of the ground is calculated, only a limited thickness of soils is considered, which is called compressible layer. The thickness of the compressible layer is normally determined according to a ratio of the vertical stress increase to the effective overburden pressure. For ordinary clays, the thickness of the compressible layer is defined as the depth where the vertical stress increase to the effective overburden pressure is 0.2. For soft clays, the thickness of the compressible layer is defined as the depth where delta sigma Z equals 0.1 times sigma V. Step 7. For each P1I and P2I, find E1I and E2I on the EP curve, and determine the sediment of each layer Si. E1I is the initial water ratio corresponding to the initial stress P1I, which equals to effective overburden pressure sigma Vi, and E2I is the water ratio after compression corresponding to the summation P2I of initial stress delta Vi and the stress increase delta sigma Zi. Step 8. Sum up Si. The foundation sediment is the summation of the soil composition of all sublayers. We have introduced the calculation method of primary consolidation sediment using EP curve for a thin homogeneous soil and a thick heterogeneous soil. Now, another method to calculate the primary consolidation sediment will be presented, which is based on in situ elogopy curve. The following two problems should be firstly resolved. One is to understand the effect of disturbance on the elogopy curve. The other is how to obtain the in situ composition curve, reflecting the in situ characteristics of the soil. A soil specimen will be remodeled when it's subjected to some degree of disturbance. This will affect the water ratio and the pressure relationship for the soil. This figure shows the laboratory compression curves of soil specimen with the same initial water ratio and the different degree of sampling disturbance. It can be seen from the figure. The higher the degree of the sampling disturbance, the lower the compression curves, and the more unclear the curvature of the compression curves will be. The consolidation curves for an undisturbed specimen and the corresponding remodeled specimen intersect nearly at a water ratio of 0.42 times E0. E0 is the initial water ratio of the soil specimen. Due to the effects of sampling and preparation the specimen in odometer test, the soil will be slightly disturbed. The laboratory compression curve cannot reflect the in situ characteristic of the soil. So, we have to determine the field compression curve. Usually, it can only be approximately derived based on the features of the laboratory compression curve. For the normally consolidated soil, the slope of in situ compression curve BC is equal to compression index CC. For the over-consolidated soil, the field consolidation plot will take a path dBc. When the applied pressure is less than the pre-consolidation pressure, the recompression path in the field is dB and is parallel to the laboratory expansion curve. So the slope of dB is recompression index CR. When the applied pressure is greater than the pre-consolidation pressure, the in situ compression path is BC, which the slope is CC. We can obtain the in situ compression curves for normally consolidated soil and over-consolidated soil. Now, let's discuss the calculation method of primary consolidation settlement using in situ compression curves. For normally consolidated soil, this figure shows the in situ virgin compression curve of the S soil sublayer. Before the stress increase, delta sigma I is applied. The vertical effective overburden pressure in the field P0I equals to average effective self-weight stress sigma Vi. When consolidation of the sublayer and the average stress increase delta sigma I fully completes, the change value of the water ratio is delta EI. Substituting the delta EI into the following equation, the settlement of S sublayer can be obtained. For the over-consolidated soil, two cases should be distinguished. One case is that under the stress increase delta sigma, the final effective pressure is less than or equal to the pre-consolidation pressure. Change in water ratio of the soil will take place only along the in situ recompression curve. The settlement can be calculated in this equation. The other case is that under the stress increase delta sigma, the final effective pressure is greater than pre-consolidation pressure. Change in water ratio of the soil will occur along both the in situ recompression curve and the in situ compression curve. The total change in water ratio is the summation of two stages. Let me summarize. Total settlement of foundation is composed of three parts. The primary consolidation settlement is caused by expulsion of the pore water from the saturated soils. The primary consolidation settlement can be calculated using EP curve or in situ log P curve. The in situ virgin compression curve can be approximately derived based on the laboratory log P curve. Thank you for watching.